Um, just a little question about one of the slides. Um, you mentioned about the proportion of the emissions of international flights and
yes,
navigation.
And
yes,
ship
ships.
and
International
flight.
ships. Yes.
Yes.
What do you know if the IPCC is going to change the way that they are taking into account these emissions? Because until now, these emissions doesn't belong to
the total.
Yes, it's not for country per country.
Yeah, I don't know. I know that they are very important, but I don't know how they could consider, because some countries they already consider the emissions by ships and flights.
Yes, but
not.
Yes, in the communications they don't belong to no countries.
Yes, and most of the related to the flights.
Yes.
It's very complicated because it's estimative based on the total consumption of fuel, and I think the data is available, because there are some associations of traffic air flights traffic control that they have this data. They have the wow. I think they have the data of the are you hearing? It's okay? No. They have the data because they have the number of flights, the type of the airplane, the engine of the airplane, and then they have the total of the fuel. But it's complicated because it's in the column. It's not emitted on the surface.
Yes.
And for the ships, it's even worse because at some cities they have more control on the ships that goes to the coast. They have to use more clean oil, and others no. They can use oil that's very poor in quality, poor oil, and then it's complicated to have this evaluation.
Yes.
But I think there are some references that can be used that evaluate the contribution from the ships.
The thing is that most of those emissions come from developed countries.
Yes. Yes. No, even even this kind of global emissions, they have this estimative, but they are not being considered. Most of the time, they are not considering these reports. No.
Okay. Thank you.
I just wanted to make a comment on one of the slides you had early on in the first part of your presentation about per capita emissions. And I think Canada was first, yes, and the US is second. From my knowledge, there were some countries missing there. Data from the International Energy Agency would suggest that there are other countries like Middle Eastern countries, for example, Qatar, United Emirates, and a number of others, which would exceed, in fact, even Canada. And Australia, I am afraid to say, would also probably have more emissions per capita than Australia, than the US, possibly than Canada. I'm not exactly sure of the current figures, but that's from 2011. So
more recent data, you say? More recent data?
Yeah. Well, the data I've seen is from the International Energy Agency, which I'm sure it takes into account energy, but I can't remember if it also takes into account land use. But certainly countries from Middle East, some countries, which use a lot of oil for electricity, actually have worse per capita emissions. And Australia as well, because we use a lot of coal. And also we have a lot of cattle. So, yeah, unfortunately, that's the situation in my country. That's all I wanted to say.
Are you from where?
Australia.
Okay. No, you see, this is from this World Resource Institute. And I took this picture, yes, these days or this week, because what I found before, it was more related not to 2011, but before, you know. I found a lot of data, 2005, 2010, and then it's not so, we have all this data, but it's not so easy to find a place with recent data. But I will try to find this. Let's say it's in the, I will try to see that, this data, yes. Because, well, I can after try to find these emissions. Okay. Now, this, and it's going to change very fast. No, this is only to. Yes. Yeah, but doesn't matter because here it's more related to the per capita. It's like a comparison among the countries. Yeah. You are right. Yes. And yeah, we have to take care of this data because it's changing all the time, you know. Also, some of these estimatives, they can change because they can use another kind of modeling. But it's okay. And this is for this is considered the data for 2010 also for the Latin American. It can sooner can change. This is always a problem. Well, but I'd like to talk a little bit about the photochemistry and explain why these co-pollutants are important for the climate. Okay.
Professor, I have a question.
Oh, sorry.
So, are you aware of any model which is something like GAINS model for the city level emissions estimates, giving city level emission estimates?
Yes, there are others. Yes, from the it's I put these GAINS because it's always being upgraded the data.
Right.
And now they also include, specifically for South America. That's not common to have. When we go to other, in Europe, for instance, or the United States, it's more aggregate for the South America. But you have different ones. And also using EDGAR, HETRO, considering the biogenic emissions by Megan, you have all this. But usually for the South America, it's not segregated by country like this. And then and at the end, the results are not so different. But it's because of this I put against. It has more data to the South American.
Okay. I have one more question regarding emission inventory. So when you are, we are calculating emission inventories across regions or across countries, how much do you think governance, local governance plays an important role or not in terms of defining the emission, finding the emission inventories or estimating them?
Yeah, it's well, it's important. The first is important that they recognize that they have to have some kind of estimative. This is the first point, to consider that it's important to have this. Usually only in the capital cities, in the big cities, they are thinking about that. And also they have, because you know, there are different groups. Always you can find different groups that has some academic data or some academic results that you can use, like here, for instance, some papers that are studying the problem. But you have to have some official data, because it's this kind of official data that will be used for implementing control policies. Then it's very important that the cities start doing that, also to become part of the law. Because usually in the cities you have the energy sector, you have the people that take care of the transport sector. They are not the same group. But when we put this kind of thing, we need to do some emission inventory for the city. Then you have to put all these groups together, because one has the data about transport, one has the data about energy, and then it starts working. if you don't have this kind of official data, official inventory, and then even to compare with the global one that comes from outside, people are not going to do anything. Then if you have to implement something like how you are going to reduce the emissions by 25%, by 30%, you have to have a first point, a zero. Even if it's a simple one, even if it's only considering the production inside the city, even if you're not considering like tier 2, no, if you only consider the emissions inside the city, I think it's the first point. It's good, this is to wake up. Someone asked? No? Oh, okay. Well, talking about the photochemistry, I put again this figure to show that we are going to discuss the way this is CH4 is related to the production of ozone and also the role of the aerosols in the radiative process. I think some of you are very used to discuss the production of ozone in the troposphere, starting from the nitrogen oxides, the carbon monoxide, and the hydrocarbons, the VOCs and CH4. But it's I only put this here only to show that to discuss the production of ozone and also the destruction, because ozone is the main source of these radicals in the atmosphere for the oxidation of other compounds. But to have the formation, first we have to start with the NO emissions that comes from the burning of the fuel. From the NO, we have the oxidation to NO2, and then we have the production of ozone. And then out of this circle in the atmosphere. Okay? And to have the production of the ozone, we can have the whole of CO, that's not so important, and the whole of CH4. What happened here is that is also, when we are looking to the city, the main impact comes from the other hydrocarbons. But when we are looking to the troposphere, then this has an impact because the rate of production of ozone is slow. But when we are considering transport out in the atmosphere from intercontinental, then it plays an important role. This is the example of net production of ozone considering the emission of CH4. We have the CH4, and from CH4 we have this is formaldehyde, but doesn't matter. But sometimes you can find some satellite data with formaldehyde measurements. And why this is important? Because it indicated the photoactivity of the atmosphere. If you have a lot of formaldehyde, it indicates that you have a lot of photochemical process. But for us now, what is important is that through CH4, we can have the production of ozone. If you analyze the time of this production, you are going to see that it takes longer to have the ozone production. This is not a new paper, but it's only to illustrate that other picture that we had seen about the production of ozone. This is the increase, the change of ozone it was related to the increase in the emissions. In January, then we are going to have more ozone in the south hemisphere, and in July in the north hemisphere associated to the hot climate, because we need the solar radiation to have the ozone production. As we can see here, without the radiation, we are not going to have any process, photochemical process of dissociation of the hydrocarbons to produce the ozone. We need to have the radiation, the solar radiation. Okay. Some other authors, they discuss also the impacts of the megacities to the production of ozone. Considering the megacities, it's not considering, for instance, like in the other slide, the burning of biomass. It's not considering the burning, it's considering the emissions by the cities. And then for different scenarios, the increase, usually we have the increase in the considering different conditions, but only to show that we can have the increase in the ozone. This scenario was considering climate change with the increase of radiation and increase of temperature and then increase of ozone with time. Only 2 points. Well, why I'm talking about this specifically about CH4? When we look to the emissions, global emissions of methane sources, we have the natural and the anthropogenic emissions. Well, here the anthropogenic emission is higher because we are considering the agriculture of having cattle in this part, not in the natural, because it's not natural emissions in the sense that it's produced without the anthropogenic action. It's related to the anthropogenic emissions. Well, most of the emissions come from enteric fermentation, that's animals. Here. We have oil and gas exploration. Then you have the leakage of CH4 when we have the production. The best example is this exploration now of shale gas in the United States. And we have also vegetation. That's a lot of uncertainties in this estimative for the vegetation and cultivation of rice. When we go to the natural sources more in detail, we have more from wetlands, apart from oceans, termites, and hydrates. Well, I included here the definition of hydrates because I know some of you cannot know the hydrates. It's normal that because it's very specific. It's a structure in which water molecules can form a cage, like a nice cage, and has inside this cage methane molecule. And then when we have sometimes more heating or some other process, this can liberate this CH4 to the atmosphere. It's a part of the total natural sources of CH4. Okay? For anthropogenic sources, we have here energy, landfills, ruminants are here as anthropogenic sources because they are growing farms. Then we have here the ruminants. Waste, that's a problem in most of the cities. Rice, production of rice, biomass burning, and other sources. No? Biomass burning is also an important source of CH4. The sink for the tropospheric CH4 is the reaction with OH, hydroxyl radical, OH, transport to the stratosphere, that's a small part, and oxidation to the soil, that's a small part. Then most of the sink for CH4 is this reaction with OH in the atmosphere that goes to the formation of ozone and mainly to the formation of the ozone. It's because of this it's important concerning globally. Locally, if you go locally, it takes so long to CH4 to produce ozone that's not considered locally, but then it's considered more not so locally. This is a picture of monthly average for January 2016, last year. It's only because only to pay attention to the concentration. This is in ppm, but it's 4 hectopascal. It's in a high place. It will be more or less than 2 ppm the concentration, between 1 and 2 ppm the concentration of CH4. But when we look to the variation with time, here the concentration is ppb. ppb is a million, no, 1,000 less than ppm. We had now between 1 and 2 ppm. In the past, we had less than half ppm, okay? Then it increased a lot in the last years. This is looking, this is very old data. This is since 19th century. We have this increase in the concentration of CH4. This is very interesting. Is the rate of increase. Here in the 19th century, you have a decrease in the rate. It was increasing slowly because it's ppb per year. It was increasing slowly, but many reasons can be enumerated here, like the temperature, the process in the tropics, other even economic process can explain the decrease in the tax of increasing. But now it's going faster again, the increase in the emissions of CH4. Always increasing, but the rate of the increase changed since the end of the 20th century. And also, this behavior, this is observed globally and average annually CH4 concentrations in ppb since 1950, compared with projections from previous IPCC assessment. This is the new scenarios, no? And there is a problem here in the scenarios for 2000 because of this stabilization between this period, and then it starts increasing again. And then the estimative for CH4 is not correct, made by this scenario. You see, here it's important because sometimes if you consider concentration, and then you don't take into consideration all these uncertainties, you can make a wrong estimative. That didn't happen with the CO2, because this is for CO2 concentrations. You see the observations and the scenarios represent better for CO2 and are not so good for CH4, considering the last scenarios, including the recent IPCC report. For N2O, also, the observed trends, it's okay with the scenarios that are being analyzed for 2002 from this, the other previous IPCC reports until AR4. When we compare the AR4 with the data now, it's in agreement. Only for CH4, it was not in agreement. This is old data, but also from the Earth Observatory, that's the last one, showing surface methane that's in, again, from 1 to 2 ppm. In February, here a lot of here, and in this north part, related to anthropogenic emissions. And this is in the surface, this is in the stratosphere. There is a lot of there is a high concentration of methane in the stratosphere because of the long life of the methane. Then you can have a high concentration also in the stratosphere because it takes longer to react. I include in the references some from James West. He did an evaluation considering, for instance, the precursors of ozone. And then the hydrocarbons, CH4, NOx, CO. Then here is for long periods, this is for short period. And decreasing the hydrocarbons, decreasing the CH4, decreasing the precursors, how much we would decrease the concentration of ozone in the atmosphere. Remember, why is ozone so important? It's important because it's a greenhouse gas. It absorbs radiation, infrared radiation in the surface, and also it affects the air quality. Then because of this, it's very important for us to study and to know what will happen if we have some control like this, controlling the precursors emissions. When we look at these pictures, we see that for all this and most of the scenarios, what we are going to have is this color in light yellow to blue. That's the decrease in the concentration of ozone. Here we have a high decrease in the concentration of ozone when we decrease the concentration of CH4. This seems not so important, but when we try to do this kind of simulations, only considering local emissions, we are not going to have this response. If we consider the chemistry, the local chemistry in urban areas, and usually we don't take into consideration the CH4 emissions. When we are using air quality models or trying to evaluate the air quality, usually we don't consider the CH4 emissions. We only consider the hydrocarbons emissions. It's only important when we have this global consideration, because then we have enough time for the compound to be reacting in the atmosphere. Also, here for most of places, when we have the reduction of NOx, considering short response or long response, we see that we have also a decrease in ozone concentrations. It will be higher, the decrease in the north hemisphere, and in the south hemisphere not so big, not so great, because we have more NOx in the north hemisphere, and NOx is an important ozone precursor. If we reduce NOx, then it's going to be reduced the concentration of ozone. Well, this is the same. It's for the same work. But comparing with the standard, the other picture was comparing an average concentration, but here it's comparing with the standard for air quality. The standard for ozone in the United States is average 8-hour average data. Also for São Paulo, we change. You have also this average concentration for 8 hours for ozone. At in the past was the maximum 1 hour ozone concentration, but now it's average for 8 hours. When it compare here for considering a reduction in CH4, it's a significant reduction. It's 65 megatons per year reduction. Then we are going to have a significant reduction in the south hemisphere also, in Africa, and in the north hemisphere, in the reduction of ozone. And also, this is not only for ozone here. This picture I put here, but it's also is the same author, but it's for another kind of analysis, that he considered mitigation of greenhouse gas emissions but now all the greenhouse gas emissions in PM 2.5 and ozone also, but 1 hour maximum ozone. This is the total change here, separating the meteorology and the emissions. It's interesting to see, because when we look to the effect only of the meteorology and here the effect of the emissions, here is the total change. Most of the, here for PM 2.5, what's more important is to control the emissions, okay? You see that controlling the emissions, you control more the total concentration. But for ozone, this is nice to illustrate that in the future scenarios that we are going to have higher temperature, for instance, the impact of the meteorology, like the the temperature and relative humidity, will have a great impact in the total change of ozone, you see? Because we can have this reduction in the emissions, but we can have this increase in the temperature in the future scenarios that is going to have a effect. And then in places where we are going to have an increase in the concentrations because of the meteorology, the total change will be less. Then considering future scenarios, we have to pay attention to this, to the pollutant, because if we have a primary pollutant, or if we have a pollutant that's more related to the meteorology, then the effect cannot be only related to the emissions, but also to the change in temperature and other parameters. But for ozone, the main parameter is the temperature to change. And at the end, what they did is to consider for PM 2.5, for instance, controlling the PM 2.5, they discuss how to decrease the premature mortality from pulmonary disease plus lung cancer. This for PM 2.5. For ozone, the premature mortality related to respiratory diseases. Okay? And this is for different scenarios. This is the reference scenario, RCP 4.5, PM 2.5 reference scenario, and PM 2.5 RCP 4.5 scenarios. This is for global, and separating for North America, Europe, Africa, Asia, and East Asia, North and East Asia. Comparing the reference scenario and comparing the closed here, the blue and the red. These are for PM 2.5, and this other here for ozone. What we see most of these future scenarios, what we see is that for PM 2.5, a significant reduction in the mortality. Well, most of the places for South Asia and Africa, first it's going to have an increase in mortality because of this consideration of the scenarios that first you are going to have more emissions and then you start controlling the emissions of fine particles. PM 2.5 is fine particles. Then we have this first an increase and then a reduction. When we look to the ozone, we have a decrease at some places, but for Asia and Africa, an increase in the mortality related to ozone. How was this calculated? First was calculated the emissions for the scenarios. Then it was used a global modeling, but considering not only the meteorological component like temperature and humidity and precipitation, but also including the chemistry of the atmosphere to have the production of the secondary pollutants like ozone and particles. And for ozone and for particles, there are epidemiological studies that relate the concentrations to mortality and morbidity. And then they calculated the relation of the concentration with these parameters. And then we can see different scenarios showing the importance of this controlling the precursors of these pollutants, the ozone and PM 2.5. According to his estimative for these reference scenarios, that's continue the business as usual, and this RCP 4.5, what we are going to have for different countries and different continents. Most of the behavior is to decrease the mortality. Important. Here we talked about ozone and the relation with CH4. But I would like to talk more about the PM 2.5, that is in PM and also other particulate matter like PM10. Well, when we look to the greenhouse gases, we are only looking to the gas phase. But when we look to that IPCC diagram showing the relation between the radiative force and the compounds, we see that the aerosols, the particulate matter, the solid and liquid phase of the aerosols, are very important. They are important because they are involved in the cloud formation, because they are the nuclei for cloud formation. Then it's not a direct effect, but it's an indirect effect on the albedo, or interaction of radiation with clouds. Also, it has a direct effect in the climate because usually it scatters the radiation, with the exception of the black carbon. And it's also related to the public health, the PM10 and PM 2.5, the chemistry of the atmosphere, visibility, ocean fertilization, that's bringing the iron bringing the iron to the ocean. Then we have many processes. I put here the definition only to make a common concept that what we call atmospheric aerosols are particles that have from tens of angstroms to several hundred micrometers. And usually what we have is particle less than 2.5 is referred as fine, and those that are greater than 2.5 as coarse particles that goes from 2.5 to 10 micrometers in size. When we consider aspects of scattering the radiation and interaction with radiation, we are talking about these particles less than 2.5 micrometers, because the others are not so related to the scattering. So, this an illustration of some particles and the size of the particles. Here is particles until 1 micrometer. Here is particles from 1 to 10 micrometers. They are the biggest particles, the dust, sea salt, pollen, that come from vegetation, from sea spray, from soil resuspension. And these others, like soot, is composed basically of black carbon, elemental carbon. Here we have sulfuric acid, that is the conversion of SO2 to sulfate. We have here a bioaerosol, it's an organic aerosol, ammonium sulfate, that's very common to find in urban areas. Organic marine aerosols, that comes from phytoplankton, others biological activity in oceans, and biomass smoke, that's a combination of black carbon and other organic compounds. We have all these emitted to the atmosphere. How they impact the climate? They impact because most of these particles, we believe, scatter the radiation. And these particles, like that has sulfuric acid, ammonium sulfate, they are good as cloud condensation nuclei. And then indirectly, they also help scattering the radiation. Okay? But we also know that soot and this biomass smoke can also absorb radiation in short wavelengths. This is solar radiation. It's not absorbing infrared radiation like the greenhouse gases. It's a different process. It absorbs the radiation that comes from this, from short wave radiation. Is it okay? Can you understand this? Okay. Then these particles, they play this important role. Why I'm showing this kind of diagram? Because for aerosols, all this process takes time to happen, and they happen in the atmosphere. When we have first some emissions of gaseous compounds, these gaseous compounds goes to the atmosphere, and there they some condense, forming smaller particles, very small particles. When they condense gas and gas, then after that we can have some particles that suffer coagulation, that get together. These particles can interact with precipitation or can interact inside the clouds, forming the clouds, inside being as condensation nuclei. These are what we call small, fine particles, that's PM 2.5. The PM 10 are related to particles that have another kind of origin, that are more mechanical formed particles, because they are formed by wind blown dust, by sea spray, plant particles. These are higher particles. It is the same illustration, only showing that this is process like formation of the secondary particles that come from the gas phase, and then they grow by condensation, then they grow by coagulation. All this process occurs in the atmosphere. When we measure the particles, if we were measuring very close to the source, usually we have a distribution, a very thin distribution. When we are measuring far from the source, what we are going to have is the increasing of the distribution, because we are going to have more smaller and bigger particles, and then we are going to have increasing the distribution in the size of the particles. Well, the particles that interaction more with radiation, with, for instance, solar radiation, is the particle that has the same size of the visible radiation, for instance. That's between 400 to 900 nanometers. Okay? Then it's the particles that are even less than 1 micrometer, that's less than half micrometer, that interactions with radiation. Most, no, not only, but most. For instance, here I will include some data from soil emissions that are very important, significant. This is a dust storm generated by this northwesterly wind. This is a satellite image from NASA, transporting all this dust for the ocean. Usually, when we look to the composition of this dust, what we have is this kind of things. No? It's iron, calcium, aluminum, silicon, the composition of the particle. Why this is important? Because this kind of compounds, they are not hygroscopic. Then usually they are not nuclei for cloud condensation formation. What they are, they can be a good icy nuclei for instance. But usually the size of these particles, they are bigger than 2 micrometers in size. They are most of the particles, not all, but the most of the particles. This is from Africa. Here it's, depending on the size, on the characteristic of the soil, we have more dust coming outside or less, depending the size of the mineral aerosols. This is a microscopy of illustrating some mineral aerosols. And when we go through the composition, we have this iron, silicon, aluminum, magnesium, the composition of these particles. Remember that they are not hygroscopic. No? They are more, and also they are, if we look to the properties, to the radiative properties, we are going to see that most of this composition, they scatter the light. Works for scattering and for cooling, the radiative force. I tried to find a new illustration of this transport here. I had this big illustration from NASA, but from the satellite tones, but I entered again in the NASA, and I found only this one from 2001, showing this plume of dust coming from Africa to north of Brazil, north of South America, and Central America. When we go to sea salt aerosols, what we will observe is process of generating small droplets and some other droplets a little bit bigger. All these droplets, depending on the wind on the surface of the sea, depending also on some barriers for the waves, and then this goes. All these aerosol go to the also contributed to the total mass of the aerosols. When we look to the inventory, the total inventory, we see that for in terms of mass of aerosols, most of the mass, more or less 90% of the mass of the aerosol, come from natural sources, from soil dust and from sea salt. When we look to the number of aerosols, number of particles, 90% of the particles come from this secondary process. What happened is that the secondary process, the formation of sulfate, nitrate, and also the emissions of black carbon and organic carbon, all this process, they form very small particles. And then in terms of mass, it's a very few amount of mass, but in terms of number, it's more or less 90% of number of particles come from anthropogenic emissions. But the natural particles respond more for the mass of the aerosols in the atmosphere. Okay, it's okay? It's possible to understand? Then and different from the soil dust, the sea salt aerosols, they are very important as cloud condensation nuclei because they have sodium chloride, and then they are important as cloud condensation nuclei, and they form bigger droplets than these urban aerosols because the urban aerosols are smaller in size. Okay. Then we have this kind of, usually we have this composition, typical composition that we expected to have. This is different sizes. Nucleation mode is until 0.1 micrometers. Accumulation mode is from 0.1 to 1 micrometers, and coarse mode higher than 1 micrometer. I put this here to show that the secondary formation, like sulfate here, coming from fossil fuel, and black carbon, and organic material, can be very small in size. Okay? Also, they are present here because of this process of conversion, but we are going to find in very small sizes. This iron here is not related to the soil. It's related to the emissions of fossil fuel burning, zinc also. And when this is for fossil fuel. For biomass burning, we also have black carbon, these particles. We have organic matter also, and other compounds related. Potassium and phosphorus is related to the vegetation, also sodium and other compounds that are present in the vegetation. And when we have the burning, it goes to the atmosphere. Okay? Well, if you look, I'm going to take two examples of aerosols. One is the sulfate aerosol. Oh, sorry, there's two sulfates, but it's the sulfate aerosol. We can have direct forcing of the sulfate. Is an example of aerosols that can have the direct forcing. Indirect forcing with formation of clouds. And also in the atmospheric chemistry, then we have these emissions, and then the sulfate reacts with other compounds like ammonium and produces ammonium sulfate. And then there's an indirect effect in the atmospheric chemistry that will impact the forcing. And also the aerosols that are formed, they can be like a place to increase the reactions, to make the reactions, the chemistry reactions more efficient because they have a surface for happening these reactions. This is like thinking about this direct and indirect effect. We have the CO2 gas, then the CO2 produces the sulfate, SO4. This is like a haze, but it can be in atmosphere like a small aerosols in the fine fraction. This sulfate aerosol, it's has the whole of reflecting the radiation, is scattering the radiation, the solar radiation. This is the direct effect. When we go to the indirect effect, what we can have? We have two examples here. One is SO2 that comes from industry, from volcans, from also burning of fuel from transport sector. All this can emit SO2 to the atmosphere. This SO2 that's in the gas phase can form the sulfate and also can be a cloud condensation nuclei. That's the first step to form the clouds. And then these clouds can also have an impact reflecting the solar radiation. There is another source of sulfur to atmosphere that's very important, is the marine phytoplankton emitting DMS, that's dimethyl sulfate, to the atmosphere. That in the atmosphere converts to SO2 and then can be also a cloud condensation nuclei and can have this impact. Also, there is a discussion if we increase the production. One of these suggestions for controlling the impact of the heating, the greenhouse gas, would be increase the production of the phytoplankton. If we increase here, then we have more DMS, we have more SO2, and we have more clouds, and then it increases the scattering of the radiation, decreasing the heating, decreasing the temperature. Some discussions, because what happens if you increase the apport, the income of iron to the sea, we could increase the marine phytoplankton production and then increase this process here. This for sulfate. Okay, with this diagram? Okay, some questions now? Well, while we have the sulfate increasing the scattering of the radiation, the other example is the black carbon. This is the opposite. The black carbon, we had here some reports, some references from two. Well, we have more, but I put here this one that's a very short paper. explaining that if we control the black carbon, that's what I said before. Black carbon is very important in a global scale, and they show that black carbon can be the second major responsible for the global warming, being behind only for CO2. This is an illustration of this particle of black carbon. You see here that most of the composition is carbon. And when we look in a sample that has a great participation of black carbon, it will be really black, the surface. And also, this is in other authors also shows the impacts of the aerosols, not only increasing the scattering and decreasing the radiative forcing, but also the impact of the aerosols for heating the atmosphere. It's interesting to show here this. They show this picture. What we have here. This is black carbon, the direct effect of black carbon. This is non-black carbon, this direct and indirect effect of the aerosols. Considering the surface and considering the atmosphere, consider both compartments. When you consider the effect of the black carbon, you have a positive radiative forcing. When you consider the effect of the other aerosols, we have a negative radiative forcing. Here is the radiative forcing for CO2. They made this estimative showing that the radiative forcing for CO2, considering the surface and the atmosphere, is 1.7 watts per square meter. When you consider the black carbon direct effect of the atmosphere and of the surface, is 0.9 watts per square meter. If you consider the aerosols without taking out the black carbon, the aerosols will be minus 2.3 watts per square meter, the average radiative forcing. Here is the top of atmosphere, because the process can be considered not only the atmosphere, but also the surface that has some impact in this calculation. And this author, they said then the black carbon can be considered having a great impact in the radiative process, in average. Well, I don't know who asked me, but about this, if people are considering or not these pollutants, these co-pollutants, related to climate change. There is one report from United Nations for protection of the environment. That is, well, there are two reports. One report is the complete report, and one is the summary for decision makers, pointing the importance of studying the black carbon and controlling the emissions of the black carbon, and controlling also the production of the tropospheric ozone, not only to consider the greenhouse gas, but also these co-pollutants. Have you seen this reference? It's a reference including some estimatives of emissions, and also the importance of controlling these emissions, particularly these emissions. In literature, we are going to have two different kind of classifications. Black carbon, that's soot, is only elemental carbon produced in high temperature process, like in the burning of diesel, for instance. For us, it's a big producer of black carbon. And brown carbon, that's a combination of secondary organic aerosols, not only carbon, but also organic, other compounds, other organic aerosols. also coming from fossil fuels and from biomass burning, but the process is not so high temperature, because in high temperature you are going to have the CO2 emissions, CO and soot. And when the temperature is not so high, depending on the fuel, you are going to have not only the emissions of black carbon, but also have the emissions of secondary organic aerosols. Primarily, we are going to have the hydrocarbons emitted to the atmosphere in the gas phase. And then when going to the atmosphere, these hydrocarbons, some enters in the formation of ozone, and some part of these hydrocarbons forms the secondary organic aerosols. And it has an impact in the radiative process. It's not, this brown carbon, it's not completely absorbing radiation. When we have the expression for defining if a compound is absorbing or scattering the radiation, we can have a compound that part of it is scattered and part of it absorbed. That's the case for the brown carbon. Here we only have the absorption factor. Here we can have the absorption and the scattering fraction inside the same aerosol. This is a researcher, Tam Bond. She prepared, like the IPCC for the greenhouse gases, a diagram for black carbon forcing, the direct, indirect effects. For instance, here, the direct effect of the black carbon is the radiative forcing is positive. And it's interesting, here it shows if it's fossil fuel, the source, biofuel, and open burning. Open burning is biomass burning or open burning for cooking. Then you have here more or less almost the same, but the fossil fuel is a little bit bigger, the participation. And the total here, it's the climate forcing is positive radiative forcing between, it's 1.1, it's a little bit different from the other paper that shows 0.9, here is 1.1, but it's almost the same. And the effect is direct effects, absorbing radiation, or indirect effects in the clouds, in cloud droplets, breathing. In clouds, there is a semi-direct effect that takes some negative radiative forcing. And here, the black carbon effect in snow and sea ice. There is an initiative also to work with the impact of the black carbon in the snow, even in the Andes, because of the deposition of the black carbon mainly from biomass burning in the Andes, decreasing the albedo of the ice surface. Considering the total emissions, now it's more or less, it's an estimate of 9 megatons globally per year. Most of the emissions come now from open burning, that includes biomass burning of forests. Then we have the transport sector and the residential sector with, here most is for heating and for cooking, the emissions of the black carbon. Okay? Transport sector, most of the black carbon that comes from transport sector is related to the diesel emissions. And the industry is when it uses coal, or more if it's using coal for generating energy. Okay? But until now, the burning, the open burning that includes the biomass burning, is the biggest source of black carbon. We could think, oh, why this is related to the cities or to the whole of the cities in the emissions? Well, we are considering that black carbon is really very important. And when we look here, you say, well, most of the emissions is not coming from urban process. It's true. Almost half is not coming from urban process. But the transport sector, most of the transport sector, is in urban areas. And these residential emissions are also related to the most with the urban areas also, with the use of fuel for cooking and for heating, globally considering. It seems that sometimes that's not so related, but it's very related. Here, it's this brown atmospheric brown cloud that is this when you consider the black carbon and also this brown carbon. We have a mixer. It represents a plume of pollution, and pollution that's coming from burning of fuel or burning of biomass, basically, no? Because we see that this brown carbon is considering black carbon and also secondary organic aerosols. Okay. This is a picture. This satellite, it is for it's for India, no? And one way of showing the impact of the aerosols is looking to the AOD, that's aerosol optical depth. Sometimes this is very usual to have this data, because it's a data that comes from satellite, and sometimes you don't have the measure at the surface, and then you look to the satellite data, and you don't have the concentrations of the particles, but you have how much of the radiation in these wavelengths is or absorbed or scattered by the aerosols. And if this number is higher, it's showing that more aerosols we have, because more of the radiation is interacting with the aerosols. Okay, this is one of information that is very useful, mainly when we don't have the data. When I put this picture here, and I including put some definitions here, because there is there are many people using the information from satellite to make this comparison with the emissions inventory. You know, because for some place we don't have enough data. I will show some data, some air quality stations data. Well, for greenhouse gas, we have almost no data. For air quality measurements, we have some data. But how to compare the measurements with these emissions inventory? How to see if they have some consistency? One way is using the satellite data, because the satellite data you have all the columns, and then you can relate this data with the emissions profile for some pollutants. And also it can be used to estimate the impact of the pollutants on the health, because, for instance, this is related to the particulate matter, to the aerosols, but you have other data for other pollutants like CO, SO2, other data. No? Then it's useful information. Then you can see in this picture where we have the highest concentrations of particles. Okay, considering smaller particles that interact more with this wavelength. In this, looking to the black carbon and looking, considering all the words, there is some estimatives that are very likely, but uncertainty in the magnitude, and some are not so, some are more likely or not so known the effect. You know? And like, for instance, considering that the absorbing aerosols can change the circulation pattern, this is difficult to prove. But what I consider here that's more easily to be verified is the interaction with this surface of snow and the interaction with the clouds. The sources of the black carbon, they are illustrated here: open burning, agricultural burning, residential cooking and heating, it's an important source, transport sector and off-road vehicles also, and industrial emissions. There is a good illustration here. It's from an old work, but showing the impact of the black carbon on snow. I took from this site, from this lab from France. It's a theoretical analysis. Here they have the wavelength in micrometers, and here is this albedo and different surfaces. Here is albedo 1 if it's only snow, pure snow, and if we increase the deposition of black carbon, of particles with black carbon, if we are increasing the deposition of this black carbon, then the albedo is decreasing from 1 to 0.2. Here it's from 0.4 to 0.8, 0.9 is the visible radiation that's interacting with this deposition of black carbon on snow. Then we are going to have a decrease in the albedo. If we have a decrease in the albedo, what we expect to have? The effect is not directly in the radiation, but if we decrease the albedo, then we are going to have less radiation scattered by the surface. No? And this, there are initiative to collect samples of snow in the Andes, not only, also in Europe, to analyze this deposition of black carbon on snow. It's there is a group, it's people that likes to go climbing, and then they are collecting samples and analyzing with very simple devices to study the impact of the deposition of snow. Have you read about the deposition of black carbon in the Andes region or not? No? It's an important impact, and people are trying to understand which is the source of this black carbon that's depositing on the snow. And probably most of this deposition comes from biomass burning, the origin of this deposition. But it's a concern to, it's not so easy to include in the modeling the change in the surface, because we can change the concentration of pollutants in the atmosphere, but this is the effect of changing the surface. And then the albedo that would be expected to be much higher will be much lower, and then we are not going to have all the scatter of the radiation that we expected to have. Okay. This is based in different references, and I have to include this, the complete reference here. But this is very interesting. Have you seen this picture before? This picture shows, it's until this point here, it's very, very frequent. We see the variation in the temperature related to the temperature between 1890 and 10, okay? Then this would be the average, and then this is showing the increase comparing to the temperature in this period of time. And from here, to 2050 and more here, it's a simulation considering measures to reduce the emissions. For instance, here, it's if we reduce the emissions of CO2. These measures here is related to the reduce the CO2 emissions. Then, if we consider the reduction of CO2, we are going to have this increase in temperature. Well, this is a reference scenario. I'm not talking about the scenarios that were chosen here. But if considering these different scenarios, but only avoiding the emissions of CO2, we are going to have this decrease in the temperature related to the reference scenario that would be with total emission of CO2. And here in blue is we control black carbon and CH4. If we control black carbon and CH4, we are going to have the same effect of reducing CO2, but it's going to be the reduction in the increase in temperature would be faster. You see this blue line here. And then if we include the reduction in CO2, in CH4 and black carbon, then we are going to have much higher decrease, bigger difference between comparing with the reference data, and this will be faster, the decrease in the increase in the temperature, if we apply some ways of controlling the emissions, not only of CO2, but also CH4 and black carbon. Thinking about controlling the temperature. No? And where we can reduce these emissions, where we can reduce the emissions of black carbon and CH4. We can think about this biomass burning, that's not urban, but also the urban sources of these compounds that are related to burning of fuel, to burning of in the transport sector also, and for CH4, also in the exploration of oil, gas, and waste. Okay? Is it clear, this picture? Okay, it's clear? Well, here we talk about CO2, CH4, black carbon, and to explain a little bit about these organic aerosols that we call brown carbon aerosols, then I include some data here related to the secondary organic aerosols and the primary biological aerosol particles that also are emitted to the atmosphere. For the organic aerosols, we are going to have these secondary organic aerosols, primary organic aerosols, and biogenic secondary organic aerosols. The primary organic aerosols include some biogenic aerosol, and here is the anthropogenic secondary organic aerosols emissions. We are going to have these primary aerosol emissions, higher emissions here, but it's a very large estimative. This is biogenic secondary organic aerosols. Only the secondary organic aerosols that comes from burning of fuel are related to this brown carbon. This primary and organic aerosol and the biogenic aerosol also, they are more related to the scattering. For instance, here we have the emissions of hydrocarbons from industry, from transport sector. We have emissions from biogenic sources. All these compounds go to the atmosphere. Usually, these aerosols are related to scattering because of the clouds. You know? And also these primary organic aerosols that come from vegetation, and some part of it from fossil fuel. When we have the burning of the fuel, we are going to have this brown carbon. When we have these emissions directly from plants, here it's from fossil fuel and biomass burning, then we are going to have this brown carbon. And we have this evaporative process or vegetation process. We are going to have these secondary organic aerosols and primary organic aerosols, but not without burning, they cannot be considered brown carbon. No? Like here, that comes from biogenic emissions and from fuels. Then we have the formation of these particles, and these particles works as scattering particles emitted by process. The natural process of formation of secondary organic aerosols, like from isoprene, monoterpene, sesquiterpenes, these compounds here are important precursors of secondary organic aerosols. These are natural aerosols. These natural aerosols, these compounds form these natural aerosols that have an impact of scattering radiation, because this will form the secondary organic aerosols. I am going fast to have time for us to discuss. These primary biological particles, aerosols also, that can be pollen from spores, plants, bacteria, all these can be in the atmosphere and also contribute to the impact with the radiative balance, because some of these are also cloud condensation nuclei, and other can help in the scattering of the radiation if it's very small, or work as more bigger aerosols. Well, this I put to discuss a little bit about the aerosols and the impact of aerosols. Is it okay until now? Because if you have some questions. And I include some inventory for Brazil as an example of the impact of the, returning a little bit to the questions of cities, to show some example. No? Here in Brazil, most of the big cities are on the coast. Here is São Paulo, Rio, but we have also in the northeast of Brazil, like Salvador, Natal. All the biggest cities are more concentrated close to the coast. This is the central part of Brazil is less populated. Then, when we put the emissions, we put more the emissions related to transport sector and the energy process in the area correlated to the population. But, but when we're thinking about the emissions by the biomass, I will show this after, we have more emissions in the central part of the country. You see, this sort for being Portuguese, but I took from the report that's in Portuguese. For CO2 emissions, it's interesting to see the decrease, but this decrease in the emissions of CO2, one part of the decrease is related to the economic crisis, no? And also with the decrease in the emission by the biomass burning, because this is changing in the soil and the forest, land use change in the forest. We have this decrease, and also the burning here, and also the decrease in the energy emissions. The CO emissions also, well, it has a decrease in the last years. It was increasing, but it has decreased as in the energy sector, also in this process, in the agricultural process. It was increasing, and then it was decreasing for the total of emissions. And this is to show, it should be before, but this is a satellite image of the burning. This is Brazil, but also South America, and some part here we have this burning of the biomass. This is not a new picture. It's from May 2016, but it's possible to have this more recent, even for this year. It's very common to have this kind of illustration with a high amount of burning. You see that is in the central, is in the north part where we have the forest, and then the central part of the country. Then the biomass is related not to the urban, but to this central part of the country. But sometimes we have this burning of waste and some small fires inside the cities, and also the burning of wood and other products. I will talk a little bit about this, and then I will. Because if we control the emissions of the greenhouse gas, we are also controlling the emission of the co-pollutants. And according to the World Health Organization, the report in last year, they had a report in last year that they have a report related to the ambient air pollution, but they also have a report related to this global impacts related to the climate change. They say that they expect to have warmer and more frequent hot days and nights that can impact the health. But in some parts of the world, and in other parts, we have fewer cold days and nights in many parts of the world, because you have in some places we have more frequent warmer and hot days, more frequent increases in warm spells and heat wave over most land areas. This is dangerous for the health. Increased frequency of heavy precipitation, increase in the areas affected by drought, and the tropical cyclone activity in some parts of the world, and increase the incidence of extreme high sea level in some parts of the world. Why it's related to the Health Organization? Because all these have impacts on the health. If you have this, for instance, this heat wave, we saw even in 2015 that the elderly people and some people that have some disease can be affected and can increase the mortality. Also, if we have heavy precipitation, after the precipitation, increase the incidence of diseases related to the mosquitoes and to the transmission by the water, like leptospirosis, for instance. If drought, it's simple, because if you have drought, you have not water, it's not treated water. And all these aspects induces the occurrence of increase in the diseases, and then they have this concern about these aspects that will be the other part of the problem. The cities can increase the emissions of the pollutants, but also will suffer the effects of all this, of the climate change. And another thing that is important in the world that we don't have for the greenhouse gases so organized is this ambient air pollution database. They put all the data in the last version is 2016 by region, and now this is the number of towns and cities where they can find data related to the air pollution. In the Africa, Sub-Sahara, 39 number of cities that there is available data. In the Americas, America's low and middle income countries, in HEIC, high income countries. Then here is America high income countries, more stations measuring, Eastern Mediterranean, low income and high income, Europe high income countries, you are going to see that we have the measurements in the most measurements in the high-income countries, and if we sum all these, we are going to have in the North Hemisphere. We have much less data in the Southern Hemisphere. This is for cities. Considering the countries, the number of countries that have data in all over the world, it's 103 countries. It's very few. The number of countries in each region that we can, for each region, we have 194. From this 194, we have 103 countries with some data related to air pollution. When we look to the average concentration, this is the data. It's not it's the number of towns and cities with data. There's only the data that was before. For Europe, we have more data, and for North America, for the high-income countries, for PM10 and for PM2.5. For PM10, we have more data because it starts being measured earlier than PM2.5. PM2.5 has standards for most countries, only for comparing to PM10 for much less countries than for PM10 because the importance was discovered much recently, the importance of these fine particles that are formed by secondary process. And this is the location of the monitoring stations for PM2.5 concentrations in these almost 3,000 places from 2008 to 2015. It's not so good to see, but one important point is the number of measurements. Most of the measurements are in the North Hemisphere. We have few measurements in the South Hemisphere, if you consider here Brazil's, most in the southeast of the country, some in Chile, I think here is Buenos Aires. Africa also we have few data, most in these countries here, but in the north of Africa, very few information. Australia, most data comes from the coast, and here it's possible to see how increase the number of stations or the data in China and also India, and Europe is well covered by data. And here it's in green or yellow is the concentration less, this green and yellow, less than 20 micrograms per cubic meter of PM2.5. The World Health Organization recognizes that the annual mean should be less than 10 micrograms per cubic meter. But it's very difficult to have these concentrations. And when we go through red points, we are going to have higher concentrations of the PM2.5 that's related to this air quality related to the air quality. And most of the composition of this PM2.5, part of this PM2.5 is black carbon. For instance, for us, 30% is of the PM2.5 is black carbon. The same happens to places where there is the burning of coal and biomass burning. Part of the PM2.5 is black carbon. It's very difficult to have this estimative because there is the lack of measurements of black carbon. We have some measurements of black carbon, but not in many places. But we can consider that part of this PM2.5 is black carbon that's being emitted to the atmosphere. Okay? Well, I think I will give some time for discussions. I would like only to, because I have some concentrations of for PM10 for other cities, but I think it is important to have some discussion about this data. I only like only to put here. This data is not so important because it's about São Paulo. I am going through this very fast. He has not shown me. But I'd like to have some points to finish, to be possible to discuss a little bit more. No? Well, I present different information, but I think one important point is, as a message or as a thing for us to think about, is that the mitigation of the greenhouse gas and air pollutants will help not only control climate effects, but also control the health impacts. And then they like this expression, that's a win-win. Then if you are going to it's not like if you are controlling one, you are having problems with the other. No, if you are controlling the emissions of greenhouse gas, you are going to control the emissions of air pollutants, because they come from the same source, the burning of the fuels and the biomass burning and the process for cooking. No? And another point is that the cities are important drivers and will be even more important with time due to the increase in the urban populations. They are important not only as emitting pollutants, but also as establishing policies to control the emissions and to start from the cities level to the country level. Because sometimes it doesn't work if it's only from country level. Because if it is something that's by the country cannot be applied in the cities, then it's not going to work. The cities must start also thinking how they can control the emissions. The population that lives in the city and that will live in the city in the future will be most impacted by the effect of climate extreme events, like pointed before, drought, temperature, rise of the sea level will impact more the population. And this is, I have already said, that the implementation plans for controlling the greenhouse gas emissions pollutants can be more efficient starting with the city level. No? Because then it can be even more easily implemented in other cities if we start from the city level. No? I think this is the most important point. I have shown many estimatives of emissions from different regions of the world, but I agree sometimes you can find other reference that can show a little bit difference from this, because it's always changing. But I think these are important points. Other point that I consider also is this not to neglect the effect of other pollutants, the short-lived climate pollutants, like the black carbon, the particles, the SO2, in the context of global change, of the climate change. Okay. Well, I would like to have some time for you to question or to discuss some points. Thank you. Thank you.
Thank you very much, Professor, for your important talks. From the presentation, what I understood that measuring emission is a complex science, and I think that the calculation are even more, the challenging at geographical scale of a city than across the whole country. And I'm sure you know the transboundary emission. Yeah. How cities treat the transboundary emission? Are cities taking the transboundary emission into account for the estimation? If so, how? And if no, why?
I think the best way is to have these tiers, these phases. Then you have for the emissions, because one thing is the total concentration to calculate your total emissions, to calculate your concentration. Then you have to take into account the contribution from other places, from transboundary emissions, like biomass burning emissions.
Okay.
But when to do your emission inventory, you have to consider what you are emitting, and also, this is the first step, what you are emitting inside the city. The second step is how much of the energy you are having to use, and then sometimes the energy is not produced in your city, it's produced outside. But you have to take this into account, because you are demanding for that.
Okay, obrigado.
Thank you.
When you thanks very much for the lecture. It was really nice. When you talk about this biomass burning, are you talking about combustion for electricity generation?
No, it's very few the participation of the biomass. At least here in Brazil and other places, it's the participation of the production or energy with biomass burning is small. Here we have the use of leaves from the sugarcane, for instance, the bagasse for sugarcane for production of energy, but it's not comparable when we have the emissions related to that, to the burning of the open burning, uncontrolled burning of biomass.
Okay.
But it's there. You are right, but the comparison is participation is not so big as the burning of the forests or the vegetation, the open.
But that values for land use change, they were like quite high if you consider that it's only for biomass burning. Isn't it more related to this change in forest to agriculture and biomass production? Because as you said, I understood that it was the opposite. It was higher because of the biomass burning and not because of land use change from forest to agriculture.
At sometimes they consider the biomass burning in the land use change. Sometimes it's not, it's separate. Maybe it's the confusion. Because for instance, for Brazil, the emissions is 75% from biomass burning. This biomass burning can be considered in the land use change because usually it's burned to have the area for agricultural activities, you know, and then they put in land use. But sometimes it's separate in the emissions inventory. It's not together, you know.
Okay,
but for us, for instance, it's much higher, the biomass burning, like for Indonesia and for Africa, it's the burning of vegetation. And you can put this separate, or you can put in this land use and the changing of soil.
Well, okay, thank you for your presentation, Fatima. I just want just quick comment. I just was wondering, yesterday we went seeing climate. Today at the morning we were seeing PSA and several climatic indices. And I was wondering, I don't know if you have any knows that if climatic projections will consider the actually air pollutant concentration, because air pollutant concentrations impact meteorology, right? For example, the concentrations of black carbon. I don't know if the climatic projections will consider the amount of black carbon, for instance.
Yes, now it considers, because when we have the aerosols there, you have why they consider the pollutants or the aerosols? They have this, in all these models, you have the radiative process. There is inside. Sometimes people don't know that there is a scheme for considering the radiative process. And there you have to include which aerosols you have. And then you have to put that if your aerosol is only scattering, or if it's a soil aerosol, or it's an urban aerosol, and how much of this aerosol is black carbon. Then you have this inside your climate models. Sometimes you don't change, it's true. You only change the concentration of total, you make some scenarios, change the total concentration of CO2, the total concentration of the greenhouse gas, and total concentration of aerosols because of the radiative impact But inside there you have the percentage of the composition of your aerosol, you know? If it's scattering or if it's absorbing aerosol. But I agree that it's not so, usually it's not considered in this scenario. You consider the increase in the greenhouse gases, and you consider that you have aerosols, but you don't change or sometimes you change. We have many publications analyzing when you have, for instance, I don't know if you have seen that, analyzing, for instance, the decrease in the use of oil in the United States, the sulfur, the decrease in the content of sulfur. And then you have less sulfur in the aerosols, and then you have less scattering aerosols. And this should impact the climate. And then they consider this, for instance. But it's not usually, this is only usually for some specific studies. Most is related to the total emissions of, the total emission of the greenhouse gas and total emission of the aerosols. But you have there inside the number distribution of the aerosols include, you have to know the distribution of the aerosols, the size and the composition. You have to put there if it's an urban, because if it's urban aerosols or if it's soil dust or if it's sea salt, it will make a very big difference. And this is another aspect. Sometimes they don't show here, but now people work with this feedback modeling. That's when we change the temperature, for instance, change the ozone, and then you have to change your concentration of ozone inside the model. You have to have this feedback. Because you can only change the initial conditions, the concentrations, and then go and see what happened. But if you change temperature, then you change ozone, for instance. If you change humidity, you are going to change other pollutants, and then this makes a difference. But there's a lot of calculation.
My question, Professor, here is regarding one study which is looking into the effects of short-lived climate pollutants, more specifically black carbon and ozone. That study is on the effects of climate change on Indian agriculture, where they look into the effects of temperature, precipitation, and on top of that, the short-lived climate pollutants. And what they find is the effect of SLCPs is much more on the agricultural productivity compared to the climate parameters. I wonder what explains that, and how is it that the direct effects of these short-lived climate pollutants could be so high compared to climate parameters?
Yeah, it's higher, the short-lived climate pollutants. Yeah. Well, for agriculture, what we have here is the high impact of ozone for instance, for the sugarcane plantation and for other vegetation, because it's very phytotoxic. This I can think that can have a direct impact that can be noted, the ozone, and also they note some effect of other pollutants. But the only thing that I can see, it's more related to this phytotoxic impact of the pollutants, to be direct. Usually even here they are using some kind of plants, vegetation, to be a bioindicator of the pollutants, because the leaves of the plant change a lot when they're exposed to the pollutants. And then it decreases the productivity of the plantation, mainly for ozone. And also, when we have this sulfur or nitrate, you have this process of acidification of the rain. And then this acidification also change the soil and then change the productivity of the soil. I think these two aspects, the direct and then the precipitation of the acid rain. But I don't know if they have some other influence.
More questions?
I agree with your conclusion, particularly the first point. I wanted to ask you a question about phytoplankton, and you mentioned about encouraging phytoplankton in the sea to produce salt particles, and also I imagine that would also sequester CO2.
Yes.
What is your opinion as a kind of geoengineering? What's your opinion on that kind of scheme to reduce climate, global warming, for example?
Yeah. Well, I don't think we have enough knowledge to know what's going to happen. What I think is that we know very few, and now so when we go to ocean, then we don't know nothing. We know nothing, because when we compare the information, the data, always the variation, we have not so many data, but I think we understand more what is happening. But when we go to this relation between atmosphere and ocean, I think we are very, very, because they're different kind of species, and then when they grow, they absorb CO2, but then we have this aspect of temperature also that increases the activity also. I don't know, I think we don't have enough knowledge.
It's possible the risks outweigh the benefits.
Yes, probably yes, probably yes.
Thanks very much.
Thank you. According to the greenhouse gases, you mentioned a few of them, but you don't mention the CO2 equivalent of these gases, because, for example, the methane, 1 unit of methane is have more impact than 1 unit for CO2.
Yes. No, you are right. Yes. Because at some data here is CO2 equivalent is together CO2, CH4, and NO2O. Yes, you are right. But I try to show the importance of this methane also in the other process in the atmosphere producing the ozone. Yes, but directly effect is higher. Then this is a concern now in the United States related to the shale gas that I was mentioned. This emission of methane, maybe it can increase. Although although the total amount is less than the CO2 generated by burning of oil. This is a complicated estimative because you have less emission of CO2, but you are going to increase the CH4 emissions by the gas. This is an interesting aspect. Yes.
Thank you so much for the dissertation.
Thank you.
I want to ask you, today was the first time on the course that we talked deeply of the role of methane on global warming, directly and indirectly through the formation of ozone. So I would like to know your opinion about mitigation of methane.
Well, I think, this is a complicated. First, the waste. The big cities I have not mentioned, but they produce a lot of waste. It's a lot of emissions. Very few cities have some way of using this gas to generate energy, for instance. Most of this gas goes to the atmosphere. And it's here it's like that. There is an open spaces emitting a lot of methane to the atmosphere. I think this is one thing that is it could be solved. It has to be solved because we are going to gain in many aspects, not emitting and producing energy. That's an important point. Other point is this use of gas also. We have to reduce the use of fuels. I don't think another solution, not this. And also we have to eat less meat. Start being more vegetarian. No? I know that's not so easy, mainly for the Argentinian people and for us, but maybe you have to reduce, because here in Brazil, the emissions by the agricultural process and the cattle is big. No? But we can start with the waste. We can start with the waste. No? I think this.
What do you think about heat islands? Are heat islands as a result of increased air pollutants?
Sorry, I don't understand the beginning.
What do you think about heat islands?
Yes, yes.
Are heat islands as a result of increased pollutants?
Yeah, I think it can have some impact, but most of the impact is due to the change of the surface. Because we change the surface, decreasing the latent heat and increase the sensible heat. Because we put a lot of concrete, the surface is have no more vegetation. And then I think this is the first impact, is the changing of the surface. And then you have the emission by the vehicles, the heat from not only the pollutants, but the heat from the vehicles, and the heat from the other process, other industrial process. And then I think the other aspect is the pollutants. But first I think it's the changing of the surface, the changing of the configuration of the circulation, the absorption of the heat. Then, because you can have heat island even in cities that they have very few concentrations of pollutants. You know, the first I think is the process starts with the surface, and then the other aspects, including the whole of the water vapor emissions by the cars, the transport sector. You know, because they emit pollutants, but they also are emitting water vapor, and also they emit directly heat to the atmosphere.
Just to add to something I just saw in the news, in The Guardian in the UK, it says, the headline is France to ban sales of petrol and diesel cars by 2040.
No, sorry.
There is a headline in the newspapers that just appeared that says that France will ban sales of petrol and diesel cars by 2040.
Wow, that's
so
nice.
They are moving somehow to hybrid and electric cars.
But all France? All the countries?
It says just France, Macron, they just did. It's likely to be a move in the EU.
Yeah, that's really interesting. No, that's so good.
It seems that it's going to be all over Europe.
Yes?
Time frame like from 5 to 15 years or something like that.
Oh, the diesel also? The diesel. No, this is here important.
So projection says that diesel is going to disappear.
Yeah, but it's. I think it's because I was talking about black carbon, but there is an important impact of diesel. That's the emission of very small particles to the atmosphere, and the question of because here we don't have a standard for number of particles. We have standard for concentration, mass, but in Europe you have the standard for number of particles. And these diesel vehicles emit a lot of small particles, and it's very difficult to solve this because it's a characteristic of the engine of the transport. And also after these problems with Volkswagen, all this, they are saying that they don't emit, but then when they go to the street, they are emitting a lot.
Do you know if here in Brazil there is some kind of regulation with car components? You know, in Argentina, we have this problem. We have this issue that we only regulate technology car, control emissions car, when they are new, when they get out from the factories. Mm-hmm. But we don't control the evolution in time.
Yes, I know. We had a program here, but only for São Paulo and Rio also, a program that was called inspection and maintenance. And then the car should go to be evaluated each year. Go and evaluate. But the last mayor stopped this process, and now we don't have this. But this is important because what they emitted when they are new, and even if you consider that they have all the process of catalyst systems, it doesn't work properly, and then they start emitting a lot. And this kind of thing obliges the owner of the car to go and to keep the car in better conditions. For places like São Paulo that we have 7 million cars, it's important to have this kind of control.
We have this kind of control in Argentina, but only on emissions, not in the technology. But the regulation is not so exhaustive. It's not too strict.
Yes.
Yes, any car, for example, cars, all cars with a lot of soot, that they emit a lot of soot, they pass this kind of test.
Yeah. This is complicated, but this is important because this is very related to the quality of living and respiratory disease. Because sometimes they make this account. They consider that the costs of implementing some regulations, but they don't put in the same account the saving they are doing in terms of health. Because we have this here when we have more polluted days and when we have in the winter season that we have much more people going to the hospital. If you put this in the account, then it's not so expensive to implement more regulations or to oblige the car to have more control.
The World Bank says that 2% of the GDP of South America goes in the public health system because
of air pollution. Yes. If it's a huge amount, if you save this money, then we are going to save. It's not like they put only the costs of the immediate costs, but if you put this in long period, you will see that you are saving money. This is always depending what you consider in your calculation. No? And it is interesting because if you make the same account of the people that goes to hospital with because they have to the United States this the money when you go to the hospital or when you stay one day without working, you have some values there. But we don't use the same numbers here. We use numbers much less because we are not so values. You say this is really very complicated. No, the counts is very complicated. Thank you. Oh, I will put I put some reference, but I will put the presentation. I'm only completing the reference here, and any question can send me an email. Okay, now it's here. Thank you. Obrigado. Thank you.